Welcome back. So A-star search in some conditions can provide an optimal solution. And kind of the key thing here is this idea of having what is called an admissible heuristic, and that's what we're going to discuss in this lecture. So if there is a solution, A-star always finds an optimal one, the first path to the goal selected, if the following are true. First, the branching factor has to be finite. Second is the arc costs are bounded above zero, so we're dealing with positive numbers here. And the third thing is that the heuristic function is non-negative and it's an underestimate of the cost of the shortest path from a node to the goal node. So if a path to the goal is selected from the frontier, can there be a lower cost path to the goal? So let's examine the mathematics behind this. So let's say, just for sake of argument, the heuristic function for this path is 0. And so we're going to suppose, by way of contradiction, that path P prime is on the frontier. And since P was chosen before P prime and h of P is 0, we know that the overall cost to get to P and the estimated cost to the destination, which we're just calling 0 for now, that's got to be less than the cost of P prime to get there, plus the heuristic estimate of the cost to the goal from P prime. So that's got to hold. Now, because the heuristic function is an underestimate of the optimal solution, we know that for any path to the goal that extends P prime, the cost has to be greater than the sum of those things. And so therefore, by combining those two inequalities, we know that the cost of P to the goal has to be less than or equal to the cost it takes to get to the goal by selecting an alternate path. So this is how we can show optimality. So A-star can always find an optimal solution if there is one, and under the conditions that we mentioned about a minute ago. And the frontier always contains the initial part of a path to the goal. So when A-star halts, the cost of all the when A-star halts, that means that the cost of all the other paths to the goal are going to be greater than the one we selected, because when it halts and we reach the goal, we now have a precise value for the cost to that goal. Everything else that's in the frontier has an underestimate of how much it costs for them to reach the goal that is greater than the one that we finally ended up with. So let's say that C is the cost of the optimal solution it takes to get to the goal. And so if we have a f function, the cost it takes to get to P plus the heuristic estimate of the cost to the remainder, if that's less than C, then that's got to be expanded. So when it halts and we have a path to the goal, if everything else is greater than it, it's not going to be expanded. And that's what we have here. So what if they're equal? Well, if it's equal, the thing is that since H is an underestimate of the optimal cost, that alternate path that may or may not be there will still be just as optimal as the one before. So this all stems from the simple fact that H of P is an underestimate of the remainder of the path cost to the goal. So this kind of simple notion allows us to formally show all these nice properties. So how can a better heuristic function help? Well, think of it. If the heuristic function is closer to the actual cost, the time when you have reached the goal and you rule out everything else, that will happen faster. So now when we have A star with an admissible heuristic, we see that we have, the nice property of completeness that we don't get with things like a heuristic depth first search or depth first search by itself, or even best first search. So we get the completeness of lower cost, and it's because we're considering that cost function as part of the selection process. However, because we are not just simply diving down deeper and deeper into the search space like you do with depth first or heuristic depth first search, we still have the exponential space complexity in the worst case, and we have the exponential time complexity. We also have the issue where this isn't going to halt even on a finite graph, and this would be due to having cycles. But there's other techniques that actually can be used with many of the different search algorithms, including A star, that can help us get around that. So, hope you enjoyed learning about admissibility of heuristics. Stay tuned for more content.